In this video, I want to continue and finish the conversation that we had started in class about the gradient of a function and tangent planes. I left off with a really nice result about the gradient of a function of three variables, but I didn't have any chance to do some examples, so I'd like to do some now. I'll start by reminding you of the important stuff that we wrote down at the end of class. Remember, the setup was this. We begin with a function of three variables. We'll call it w equals f of x, y, and z. And by setting w equal to some constant k, we obtain a relation in x, y, and z, which we call a level surface of w. This level surface, algebraically again, is just an expression in x, y, and z. And so its solution set is a surface in R3. So we can plot the surface in R3, and we choose some point P lying on the surface, pictured here. And here's what we showed. Well, to make a long story a little shorter, we showed that we can construct lots of tangent lines at P, or lines tangent to the surface S at P. And the main result was the following, that the gradient of the function at P is orthogonal or perpendicular to all of these tangent vectors. Here we have this result written down, and I also have the gradient sketched in red, so let me write gradient f. And here's the result. If P is the point x naught, y naught, z naught, then the gradient of f evaluated at that point is perpendicular to all vectors tangent to S at P. So our approach now is the following. We might as well define the tangent plane at P to be the plane which passes through P and which has the gradient of f as its normal vector. So we'll do just that. Here's our definition. The tangent plane to S at P is the plane passing through the point P, x naught, y naught, z naught, with normal vector n given by the gradient evaluated at the point P. We can write this tangent plane in vector equation form if we denote by r the vector x, y, z, and by r naught the vector x naught, y naught, z naught. Again, r should be thought of as a variable vector and r naught as a constant vector. Then the vector equation is the following. R minus r naught dot n is equal to 0, where again n is the gradient vector. So given that n is the gradient vector, we can rewrite this as follows. Here's that vector equation written out in just a little more detail. Here is the vector r minus r naught, and here is the gradient vector evaluated at the point x naught, y naught, z naught. Let's use this recipe to do an example. For this example, let's find the tangent plane to the surface x, y, z squared equals 6 at the point 3, 2, 1. Let's take a look at a graph of the function. It's not going to help us do the problem, but it's interesting to look at the surface before we think about the tangent plane. So I've graphed the surface x, y, z squared equals 6, and this is at least a portion of the graph in 3 space. And we'd like to construct the tangent plane at the point 3, 2, 1. So we can plot that point. And here you see the point as a large red ball at 3, 2, 1. So here's where we want the tangent plane. Remember, to do this, our technique now is to obtain a normal vector, which is the gradient of some function of 3 variables. And this should be evaluated at the point. But we don't have a function of 3 variables defined. So before we do this, we need to define this function f of x, y, z, for which this surface is a level surface. So let's define f of x, y, z equals x, y, z squared minus 6. That's a definition. And now we can see that if we set f equals 0, we obtain 0 equals x, y, z squared minus 6, or rearranging x, y, z squared equals 6, which is the equation with which we began. So this is the function of 3 variables that we'll work with. In particular, this is the function whose gradient we'll take to obtain a vector normal to our tangent plane. So let's do this. First, we'll write down the gradient vector, and then we'll evaluate it at the point. So the gradient vector will simply be the vector with components consisting of the partial derivatives of f with respect to the 3 variables x, y, and z. So we can calculate that now. Partial with respect to x is yz squared. Partial with respect to y is xz squared. And partial with respect to z is 2xyz. And now we can take this expression, this gradient, and evaluate it at the given point, which is 3, 2, 1, to obtain the vector 2, 3, 12. Great. So now we have a vector normal to the surface. We can plot this vector on the surface of the function, which we saw just a moment ago. If we jump over here, here's the vector which we just generated. So this is the gradient of the function, capital F, evaluated at 3, 2, 1. And we can see if we did our job well, this looks like it is normal to the surface. Let's go back and finish writing down the equation for the tangent plane. And here it is. Remember, if we have a normal vector for a plane, writing down the equation for the plane is easy. The coefficients of the normal vector just go in front here, here, and here. And these points, 3, 2, 1, or these coordinates, are simply the points, the coordinates of a point through which the plane passes. So here's the equation of our tangent plane. You could, if you wanted, expand this and rewrite this equation in several different ways. That's it though. Let's go ahead and graph the tangent plane and see how it looks. And if we've done a good job, we can see the tangent plane. That concludes our example. So now we have a more general method for generating planes tangent to surfaces. It works for functions of 3 variables. You'll have a chance to try some more of these in the homework on WebAssign now.